Welcome back to The Explainer. Today, we're diving into a math problem. And this one's a real head-scratcher from the Australian Olympiad. It looks totally impossible at first glance. But the solution, it's not where you'd expect to find it.
All right, let's get into it. Here's the setup. 3 equations, 3 variables, x, y, and z, and we're asked to find the value of this expression up here. Now, the key thing is you don't actually need to find x, y, and z themselves, just the value of that whole thing. So your first thought, like mine, is probably to just, start crunching the numbers. Try to substitute one equation into another, isolate the variables. But trust me on this one, that is a deep, deep rabbit hole. It's basically an algebraic dead end, and it's designed to be that way.
So if algebra isn't the answer, then what is? Well, when you hit a wall like that, it's a huge clue that you need to change your whole perspective. The secret here isn't buried in the numbers at all. It's hidden in the geometry of the problem.
And the key that's going to unlock this whole thing is something you probably remember from trigonometry class, the law of cosines. It's that neat little formula that links the lengths of a triangle's sides to the cosine of one of its angles. Super powerful stuff.
Okay, so check this out. Let's take our first equation and put it right next to the law of cosines. See the resemblance? If we just tweak it a little bit, suddenly it's a perfect match. That 25 is just 5 squared, and we can rewrite that middle term to fit the formula perfectly.
And this is where it gets really cool. Our first equation, it's not just an equation, it's a triangle. It's the law of cosines in disguise, telling us we have a triangle with sides x and y, and a third side with a length of 5. And that angle between x and y, it has to be 150 degrees, because the cosine of 150 is negative root 3 over 2.
All right, let's see if this pattern holds up. We'll do the exact same thing with the second equation. A little rearrangement, turn that 16 into a 4 squared, and yep, it works.
Boom! Another triangle. This one has sides x and z, a third side of length 4, and the angle between them is 120 degrees. Why? Because the cosine of 120 degrees is negative 1/2. It's all fitting together. Now for the third equation, and this one's even easier. Y squared plus z squared equals 9. Wait a second, that's just 3 squared. That's the Pythagorean theorem. So this one's a good old right-angled triangle with sides y, z, and a hypotenuse of 3.
So let's just take a step back. We started with 3 really messy-looking equations, and now we've turned them into 3 simple geometric shapes. 3 triangles, each with a known angle.
And here it is. This is the big aha moment. What happens if we add up those 3 angles we found? 150 degrees plus 120 degrees plus 90 degrees. That's exactly 360, a perfect circle.
So what does that mean? It means our 3 triangles, which all share sides x, y, and z, can actually fit together perfectly around a single point. It's like they're puzzle pieces, and because their angles add up to 360 degrees, they form a complete circle with no gaps.
And when we snap them into place, look at the shape they form on the outside. The outer edges, those sides with lengths 3, 4, and 5, they form a brand new, bigger triangle. And hey, a 3, 4, 5 triangle? That's the most famous right-angled triangle there is.
This is brilliant because it gives us a super simple way forward. The area of that big 3, 4, 5 triangle has to be exactly equal to the sum of the areas of our 3 smaller triangles, right? It's just simple logic.
Okay, calculating the area of the big one is a piece of cake. It's a right triangle, so it's just half the base times the height. Half of 3 times 4 is 6. Simple. And we know that 6 has to equal the combined areas of our 3 little triangles, which we can calculate using that other area formula, 1/2 AB sine C. And since we know the sine of 150, 120, and 90 degrees, we can just plug those values in. When we do, we get this new equation. 6, the total area, equals this whole expression here.
Okay, hold on. Let's pause for a second and look back at the original question. Remember what we were actually trying to find. xy plus root 3xz plus 2yz. Now, look at our area equation. Does that look kind of familiar?
It's so close. You know what? Let's just take our area equation and multiply the whole thing by 4. Watch what happens. The right side becomes the exact expression we were trying to solve for in the first place, which means our answer is just 6 times 4, 24. That whole complicated thing we started with, its value is just 24, and we never even had to figure out what x, y, or z were. How cool is that?
I mean, the big takeaway here is just how powerful it is to change your perspective. Sticking with algebra was a total dead end, a nightmare. But the moment we translated the problem into geometry, the solution just unfolded, clean and simple.
It really makes you think, right? What other complex problems, maybe in your own life, are just waiting for the right angle, the right change in perspective to suddenly become simple?